Hi everyone, my name's Jeff, as he mentioned, and my colleague Rohan is joining me to give part of the talk today. What we want to talk about is this crazy world beyond just normal everyday programming. That's typed functional programming. And to us, it's a sort of wonderland that you have to pass through the looking glass and encounter what you find there and the strange creatures. And so we're coming back from that land to report on our journeys as a team, picking up typed functional programming as part of using Spark and Scala. I want to give you a little bit of perspective on what our situation is, though, before we kind of dive into the technical material. And that is that we build an artificial intelligence. Specifically, we build an artificial intelligence that schedules meetings over email, that behaves precisely as a personal assistant. And so in that world, there are a lot of properties that probably look like your worlds, in that the scale of our work is constantly increasing, and the complexity of what we have to do is always also increasing. But we're still just people trying to manage all of this complexity. And so we have unique challenges on our plate. This is the most simplified version of our system diagram that I could come up with. And this is a very boiled down view. The real one, I actually looked it up. It was hundreds and hundreds of boxes and lines containing so much proprietary technical detail I could never show it to you. But in fact, everyone has to work with that on our team every day. They have to think about all of those different system components, all of those different data flows, and what they're trying to achieve, their specific missions. That real-world artificial intelligence has tremendous system complexity. And it has that system complexity for a very specific reason, is that the problem itself is that complex. This is a diagram of a dialogue model. The specific plot here is a Sankey plot. And so what we're seeing here are the different dialogues that the artificial intelligence has taken over time. And so fat, short dialogue trees there indicate that we've been very successful and we've taught the intelligence something very useful that it's able to achieve quite easily, whereas the spindly, spaghetti-looking lines indicate areas in which we still need to do future development. This is a really hard level of problem to keep in your head, as well as, so when you actually try to implement machine learning intelligence functionality to make those decisions, to speak those words in natural language, you wind up building things that are really already kind of beyond your ability to think about them in a sort of really coherent way. This is a projection of a deep learning model into a word cloud of concepts that Amy understands, the artificial intelligence that we build. And so there are expressions in here that you can see if you check out the higher resolution version on our website, where you'll see clustering around temporal expressions and things around names. But this is just a sort of hint at the complexity of what we have to build. And so the point of all this is, all we can build this with is people. And so when trying to build a team of people who can build an artificial intelligence that has this sort of system complexity, inherent domain complexity, you need a certain sort of person, and you need to make them successful in a certain way. I call this concept a data knot. That is someone who is both fully capable of doing all this data engineering work and all the data science work that allows a person to conceive of how can we construct different components of a machine learning system in such a way that composes up into a highly functional autonomous agent. And so to do that, we've, as a team, chosen specific tools, specific technologies that allow us to succeed in that journey and help people get down that path. And that's really the focus of what I talk about today, is for those people who choose to embrace that challenge, how are we making them successful? What are some of the steps along the path? Because it might look like that on your team, should you choose to use the same tools that we use. So first and foremost, we use Scala, as I would imagine a large chunk of you all do here as well. And we do that for specific reasons, and I want to highlight that Scala has this unique property of being a very bleeding edge, principled, academically motivated functional programming language with a lot of specific powers that come out of that, but yet we use it in the real world, in industry. And that means that we have great support from things like tooling, documentation, training, things like that make it possible for us to build a product that we're going to sell for money using an academic programming language. All of that I just said about Scala applies equally to Spark, of course. It has the same sort of foundational motivations that come out of fundamental computer science work that allows all of the things that we are hearing about today at the conference to be possible with Spark. Building on top of those achievements that came out of the implementation of Scala itself. At the same time, this sort of community support gives us the ability to rely upon great tooling, things like Databricks Cloud and other hosted Spark platforms. So Scala and Spark make perfect sense together, as I think everyone would agree here. But we're going to take it just a little bit further and talk about another really powerful tool that we think can be used effectively to tame some of this complexity, and that is typed functional programming. Now, typed functional programming also has this great academic pedigree. There's all sorts of really interesting books that have all sorts of mathy terminology to them. But typed functional programming has sort of a bad reputation of being very hard to learn, being a very abstract and not real world and not useful sort of thing. And so we disagree. And we want to show you how you can actually build functional programming knowledge within your team and bring all these things together all the way to doing principled typed functional programming while building real-world artificial intelligence systems. So the first stop along that journey that I want to introduce you to is that strange word functions. So when you introduce someone who's new to functional programming, to functions, I think it's helpful to start with getting clear about what they might have seen before, that is methods. And so in this context, we're going to think in terms of sort of a Java-centric view. So a method is a collection of statements that can have side effects. That is, that they can change the state of the world, and they're actually kind of attached to an object. And so I want to show you what I mean by this sort of like common mental model of a method. Here we're going to build up just a generic data set, nothing Sparky here, just a Java container of some data. And so we're going to establish that we have some instance variables. We're going to construct them, construct an instance of the class, setting those instance variables. And then we're going to implement our method on the class. And so we see some mutation here. We're changing both the local state of the method, but then also the outer state of the instance itself before returning out our average value. Some reasons I don't really like this style of programming, and one of them is that it's fairly trivial to render that state fundamentally invalid by just implementing a method like this that allows you to reset what are the instances in your data set there, thus rendering the class inconsistent. And so then you must then re-execute the same method on that instance, now having changed the state of the world to be able to get the correct average in this implementation. And so this, which I realize is kind of hard to see, is just all of that code I just showed you on one slide. And that, I think, is also a part of the problem in that we in a particularly Java-centric OO view of the world, we reason about computation in this glued together way in which data and behavior can only be expressed in this collection that we call an object. So when you introduce functions, I think it's helpful to change that context and say, here, we're doing something quite different, in that functions are collections of expressions that return values. Now, there still is object orientation, but it works quite differently. Functions themselves are actually objects within Scala. And I think most powerfully at a syntactical level is, of course, that they can be inline, that there are function literals. Let's walk through that same example code, doing it a bit in Scala again. So remember, we're just writing a very simple averaging function. There is a trivial implementation here that I'll acknowledge, but I want to show you something that takes it through in a little bit more steps. So here we've implemented a function named add, and then we've used a fold here. So immediately we're describing add as a function. It is side effect free. It returns a value. And it's now higher order, right? So within that line in which we established the sum, we're passing in the function to another function which accepts functions as arguments. We're also currying there, passing in both of those functions as well, but I think that's less important. And of course, we can iterate on this. There's a lot of syntactical help for us so that we don't actually need the implementation you see in those first two lines to be quite so complex. In fact, we can take out that add function because the add function already exists within the Scala language implementation and just use it as the symbolic operator in an anonymous higher order function there, giving us a little bit of syntactical cleanliness. So with that baseline of what a function is in Scala, it's the exact same thing in Spark. It makes it very easy for someone who has built that foundation to then take that knowledge up to the exact same, to the level of a cluster in a syntactically nearly identical way. You can see that we're implementing the same averaging function here with almost the exact same syntax. We still have our higher order anonymous function. Just in this case, we're operating over an RDD at cluster scale. Okay. So once you've introduced someone to functions, I think the next thing that you're likely going to need to introduce them to is immutability. So in immutability, we want to talk about not changing things. But to talk about not changing things, we need to talk about what we mean when we do change. And so I referenced it a little bit in that Java implementation before. What did I mean about mutation? Here's a very simple Python implementation. There's no particular object orientation here. What we're doing here is we're counting up the number of visits to a given website. And so we've established a dictionary data structure, and here is one method of updating the counts of visits. So when Bacchus comes to visit the site again, we simply mutate the value. It's a pretty common programming paradigm. A lot of people with a data science background are well-versed in Python and think of this as very natural. And so this is a sort of mental model that we encounter a lot when we add new team members to the team. In Scala, we want to default to immutability. Sure, the language has the ability to have all sorts of mutable escape hatches, but we want to default to immutability. And so how do we do the same task using immutable data structures? Well, first we establish an immutable map, which is precisely the same thing as our mutable hash map from before. But then we produce a new version whenever we want to make an update here. So in this case, we're having Bacchus visit the site again and applying that to be the new record here. Taking that to the level of Spark, this immutable approach to working with data structures is still something that you can do at scale and can be quite powerful, even if there's more implications about the processing time when you use immutable data structures. So in this case, we've actually taken our base level of visits, the original ones, and we've created a single new visit RDD, and then we're using RDD operations to union those two concepts of how many visits have been made, and then using an aggregation operator. And then again, we have two higher order anonymous functions to bring that together. So that shows us how we can use immutable data structures within Spark. So I want to recap at this point because we're actually at an important point within the development of a functional programmer learning these tools for the first time. Basically, we're at the point of the functional programming you will see in certainly in dynamically typed lists like Clojure, but also in pseudo-functional languages like Python or Ruby. We've definitely introduced someone to concepts of higher order anonymous pure functions. So someone should now be capable of working with functions on a certain level and expressing their computations in that way, both within Scala and within Spark. We might have also started introducing someone to these other concepts, which are more advanced. So, for example, we saw currying. Actually, we also saw in the distinction between a method and a function, hopefully you might get a chance to introduce the concept of referential transparency, which is really important for data-intensive applications, the idea that we will get the same answer every time we invoke a computation. We're beginning to see closures in the sense that you understand that computation that you expressed in simple Scala that executed on a single node was able to be sent over a wire and passed around a cluster. And so you have a context in which to have how is that possible conversations. And finally, you're building up to being able to introduce enough concepts to explain what is a resilient distributed data set, and then thus what is Spark doing and why can it compute your jobs at the scale that it can in the face of failure. But to have that fuller conversation, you need to get into a set of more sophisticated concepts, less from the Lisp tradition, more from the ML Haskell tradition. And to discuss those concepts, I'm going to hand off to my colleague Rohan to take you on the next step of your journey.
All right, hello everyone. So I'm going to take you through the next 3 steps of our journey, and kind of to expand a little bit on what Jeff said, we'll go through lazy evaluation, typing, and then monads, and then I'll wrap up a bit with our conclusion. So lazy evaluation in functional programming is pretty important. What we mean when we say lazy evaluation is delaying the evaluation of an expression until a value is needed. And there are 2 major advantages of lazy evaluation. The first is being able to defer computation to evaluate only what is necessary when computation actually happens. And finally, changing the evaluation scheme on what the scheme that's finally been created to be something that's more efficient. So that's something we will see both in a functional language like Scala and then something in Spark, which is a little more related to the infrastructure. Moving on to the next slide. So Spark is a framework in which all transformations are lazy. And what we mean by that is we have this computation DAG that we kind of build up that attaches transformations and builds out this kind of structure where you can kind of see which RDDs come from like a parent RDD. And this DAG, directed acyclic graph, is optimized before execution using things like pipelining, the catalyst optimizer, which you may have heard in other talks or last year. And no actual computation has been done when this DAG is constructed. And when we invoke an action, we are executing parts of that DAG and not the entire DAG. So that's pretty important with lazy evaluation. And as we can see with the example DAGs, they used to look a little more complicated, which is the DAG on the right. But there have been some changes in Spark 2.0 that actually compress it and make it a little bit easier to understand. But the DAG relates back into lazy evaluation because we're evaluating only parts of it. So if we look at some code examples for lazy evaluation, here we have 4 RDDs that we're creating. The first RDD, we're just loading in some data by parallelizing some collection. And then we're doing 3, let's say, different maps on top of that parent RDD. And we are only calling the take action on the third RDD. So in this case, the computation DAG has been created for including all 4 RDDs, but the action will only look at 2 RDDs and then compute based off of that. So really, RDDs 2 and 4 here exist in theory on the computation DAG, but nothing has actually been created. To tie it together, learning laziness through Spark, we had our first advantage where we have deferred computation, and it draws directly from like that selection of parts of the DAG to compute, and only executing an action, or only computing what's necessary when you execute an action. And we have advantage 2 where you have the optimized evaluation scheme. It draws directly from Spark principles where you can reorder kind of what you compute in the DAG based off some set of computations that might be more efficient. Maybe when you're doing a join between 2 RDDs and you have a filter that comes after it, you can push the filter up to not join as much data, for example. And understanding the motivations behind laziness in Spark helps you understand why laziness is useful in functional programming, which is kind of relates back to the concept of our talk of how we're learning functional programming concepts. So now we'll get into types. Type systems, while they're not always used in functional programming, are there in, I guess, a broad class of functional languages. And they play a pretty important role. So there are many benefits to using them in functional programming. One functional concept that's pretty useful is the creation of, or using algebraic data types for grouping different elements of data into some sort of schema and creating some program structure. The data must fit a certain type if you create this algebraic data type. And it fits in really usefully and easily in pattern matching, for example, and schemas. And it also, typing also allows us to get compile time safety, which is really useful because you kind of want that safety net there before you actually run a really long Spark job and find out that you hit a compile, or hit an error that you could have caught in compile time. So moving on. Types in Spark, we have these broad class of containers, RDDs, datasets, and data frames. RDDs and datasets of which are typed and data frames are untyped. And types provide great schema enforcement for the first 2 set of containers to kind of enforce that all elements that are stored in your RDD correspond to a certain schema. And while it's not there in data frames are essentially data sets that are on top of some generic row. So you could kind of end up seeing something that you would have been able to catch as a compile time error in a data frame or in a data set with a data frame, because you may access some field and run an integer operation on there when in reality you're dealing with another type, say a string. So it's really important to have this sort of type safety net there. So when we look at a code example for types in Spark, we have this base schema that we created called a person that contains two fields inside there, a name and an age. And here we are just reading some JSON data, attaching this person schema on top of it and creating this data set. And then we can actually perform an operation on top of this data set using the schema that we created above for person, illustrating that we can use the content of the data type to run some operations on it. So now we'll kind of get into like learning types from from Spark into Scala or into functional programming. ADTs have two widely used types, the product type and the union type. And I'm sure many of you have kind of used this before, even if you may not have heard of it. For product types, they're common types that combine different fields into an aggregate composite type. And we can kind of think of this as tuples or records, which are used pretty broadly inside Spark. And then you have the union type, which consists of having some sort of super type, which breaks down into different subtypes. And we can think of classes and inheritance with union types. And it's really important to use these sort of ADTs because they help us reason about our code better, adding more structure to our program. And it also improves code comprehension as well as giving us the advantage of compile time safety to make sure that you're running the right operations on top of your data. So if we look at a Spark example here, we have now a trait person type that contains a field name in which all implementations of this person type must define name in some way. So we have two different types of persons here. We have a student and a professional, both of which implement the name field and have two different fields attached, a grade for a student and a job for a professional, and we're extending the person trait here. So let's say we have some collection, some sequence of persons that can be both students and professionals, and we decide to parallelize it into an RDD, so now we have an RDD of person. Working with this person RDD, we can map over it and case out based off whether a value is a student or a professional and do separate operations with it. So this kind of ties back into what Jeff was talking about with functions and being able to create an anonymous function and sort of map out what you want to do in each case. And here we can see that we're using union types to break out the different cases and product types to break out the fields within each union type to run whatever operations we want here. In this case, we're just extracting grade from a student and job from a professional to create a list of what people do. And then to illustrate compile time safety with types, we have a pretty simple example here. We're parallelizing some collection into the RDD person that we saw before. And we are, in the first case, we are running a map on top of the RDD and attempting to append the string name to a person, which obviously does not work because person is not a string. And in the second case, we are able to do that because we are accessing the name field inside each person and then adding or prepending name to that. So it works. So now we'll get into monads, which are people see it as a difficult concept, but with respect to Spark or with respect to Scala, it's pretty simple to understand, I think. In category theory, a monad is a monoid in the category of endofunctors of X. I won't really get into that because it sounds really complicated, and it is, but inside functional programming, it basically refers to a container or a wrapper on which you can perform different operations inside the values inside that container. So the first part of a monad is being able to inject a value into that container and have this wrapper around it. And then the next two parts consist of being able to perform operations that return a container on a new set of values, and then being able to flatten nested containers into a single container. And this can kind of be seen as two sort of operations. So there's no native implementation of a monad in Scala, but there are many different libraries that have implementations, for example, Scala Z. So the trait monad in this case has two functions, apply and bind. Apply talks about that first ability of being able to inject a value inside of a monad, where we take some, in this case, a value that corresponds to type T, and then wrap it inside the monad M. And then the second operation, bind, which looks very similar to flat map, takes in some previous monad that we had, and then takes a function that converts some value T into a monad over type U. And this kind of combines the previous two operations we talked about on transforming transforming values inside of a container and then returning a container of this new type. So Scala actually has many generic container types that are implemented as monads. In this case, I'm sure many of you have worked with lists, sets, and options before, where you can create a list by kind of wrapping it inside some sequence of values, and then you can run flat map operations on lists to return a list containing maybe a new type. And it's a very powerful line of thinking, because being able to sort of chain monadic operations and wrap values inside monads helps with code comprehension and reduces error checking logic. I'm sure many of you have seen in object-oriented languages like really complicated streams of error checking that monads kind of handle naturally based off pattern matching, which makes things really easy to read. And you can also build further transformations on monads. For example, map, filter, for each, that do different things but are also monadic operations. And many of these functions can be seen inside Spark's container APIs, which is where people are sort of learning the concept of a monad from. So in Spark, we have these computation builders, kind of what we talked about before with RDDs, data sets, and data frames. And they're containers on which different transformations can be applied. So if you have an RDD of some type T, you can apply a map and get an RDD of type U by providing a function that transforms elements of type T into type U. So are RDDs or data sets or data frames monads? Not exactly, because monads come from like a very theoretical part of functional programming in which this concept can be applied to all types, whereas RDDs can't exactly do that. You can't really lift all types into a flat map operation because you need a class tag that's attached to a type in order to put it inside of an RDD. I won't really get into that, but it's the point is basically that we can't put all types into an RDD. And there's also no unit function inside of an RDD to kind of inject values into. We have different operations to read from data into an RDD. For example, the parallelize method, or in data sets, reading from JSON. There is no like container method that can or application method that can kind of put values inside of a container though. So to wrap up, what we kind of wanted to introduce with this talk was the fact that Spark is introducing all types of developers from many different backgrounds to Scala. These can be developers from object-oriented languages like Java, or many sort of like researchy languages like Python, where data scientists usually live. And Scala helps people learn about type functional programming. As examples, some of the concepts that we've been talking about. And type functional programming really does improve Spark development by adding many of the different advantages that we talked about. As an example, like the compile time safety or improved code comprehension through typing. So a little bit about us. We're a company, as Jeff said, that loves to build artificial intelligence through models that can kind of describe or models that our product uses to interact with people and schedule meetings automatically. You can reach us at Twitter at x.ai, send us an email at hello@human.x.ai, and we're located in New York if you guys want to apply or visit. And if you join, you will get your own human.x.ai domain name, so that's pretty cool as well. And your own artificial intelligent agent, which is awesome to tell your friends. And for all Manning books, you can use the code CTW SparkS17 to get 40% off, including Jeff's book, Reactive Machine Learning Systems, highly recommended. And that's it. Thank you.
QA, we've got time for a couple of questions before lunch. Anyone want to venture a question? Nobody?
There's one up front.
Oh, you want to take it offline?
Okay. Cool.
Okay, one question. Yes.
All the way in the back.
It seems that Scala is kind of quite synonymous with being used in Spark. So does it get used elsewhere?
Does Scala get used in tools other than Spark? Is that
Right,
the question?
yeah.
The Scala community is huge and very active and in use in all sorts of contexts. I've seen it. It's popular for data processing.
Yeah, we use Scala in a non-data processing sense to build like kind of the native logic within our application as well. So it's used in many places. In fact, there are libraries like Scala.js, for example, that are attempting to encapsulate other concepts into Scala.
Okay.
Okay, guys, thank you very much.
Thank you.
Time for lunch, and we'll resume here again at 2 p.m. Enjoy.
Thank you.